So thanks again for joining us. My name is Nicole Wolter, as Cindy mentioned, and on behalf of the Complex team today, I'm going to be presenting on HPC hardware, obtaining hardware information, and monitoring performance. If this is your first time joining us for one of our webinars, I'll give you just a very brief background on the Complex program. It's funded by NSF, and it's specifically designed to focus at those folks who are non-developers or non-programmers. So over time, the HPC landscape and who's using it has kind of changed. It used to be that everyone who was using an HPC system was developing their own code. Now lots of people are using other people's codes to do stuff, but it's still important to know the tools that we're presenting in these webinars to help effectively and efficiently use the resources. As Cindy mentioned, we're developing this for y'all. So if you do take the time and fill out those surveys, it's really going to be helpful to us to make sure that we improve and keep focused and bring to you what is needed for you guys to help y'all. So today I'm going to start by revisiting a brief introduction into kind of HPC systems, and then focus on the specific aspects of those systems that affect users the most, basically, the hardware-wise. Then we're going to look at some hardware monitoring tools to evaluate if the tools are there and how the tools are being used. Then we're going to finish off a little bit on specifically looking at how individual jobs are using the system. So I think it's always a good idea when you create presentations to kind of have an agenda in mind. And I hope that by the end of this webinar, you all will be a little bit more familiar with the HPC architecture and how it could affect you. And also that you'll be able to use the available resources that we have on the system to identify what's there and evaluate how the hardware components are being used. So to start off with, I'm actually going to revisit a slide that was presented in our last webinar by Marty. And this is just kind of a high-level reminder introduction to what HPC is. So HPC, or high-performance computings, are using supercomputers or compute clusters, and compute clusters consist of multiple dedicated HPC processing nodes, and they're connected by super specialized high-speed networks. And so the high-speed network and the having lots of processors is really what makes the HPC system special. By comparison, your laptop probably has one or two processors, a couple of accelerators, whereas the HPC clusters are going to have hundreds or even thousands of these compute clusters, and they're all networked together. So by networking together, it really makes it look as one system. So it facilitates the work to be accomplished in parallel, and that allows the jobs to boost the processing speed, which allows you to solve your problems more quickly. It also allows you to scale up to larger, more complex problems, and it can scale up because by increasing the available memory and the compute power. And with the additional compute power and processors, it also allows you to push through more throughput. So many simple problems more quickly. So the first thing I'm going to touch on isn't really hardware, but it's very important it's very important connected with the hardware. So while the kernel and the operating system are not hardware, if you can identify the operating system and the hardware, it's going to help you identify the toolbox that's available to you to look a little deeper into your system. So kind of to break down the connection between the two, the kernel is the system software, which is part of your operating system. And the operating system is going to provide the interface between you, the user, and the hardware. And the kernel is going to provide the interface between the application and the hardware. So naturally, if you want to know more about the hardware, you need to know how to get there. So the tool we can use to find out more about the operating system in the kernel is the uname. And this actually stands for Unix name. If you type that without anything else, it's just going to give you the kernel name. By default, it's just going to give you that. But it's important, or maybe not important, but it's useful to be able to get a little bit more information. And so we can use the -a command, which provides us more information. It'll give you the name, it'll give you the version. You can see some other details here. One of the things that is I usually find as an important thing is to note that date. That's actually part of the name. They put it in there, and that's actually when it was last compiled. So when you come back at some point, so this can also be used not only to find out what tools you have available to you, but you can also use it to find out if all of a sudden your codes stop working. You can check to see if something changed on the system. This is a very high level thing to note, that if this changed, usually there's something else that you're going to have to look at to get your code to get working again. And then if you specifically want to look at the CentOS release, you can look in etc CentOS and it'll give you the specific release date. So let's take a quick high look at kind of the high level of the HPC components that we kind of want to talk about today. So the HPC systems are a combination of hardware and software. The hardware that we're going to look at is the processors and accelerators and the sockets, the memory, and all the attached devices. And again, this is all put together with a really fast communication between the nodes. And then there's the software and tools that will help make everything work together. So now that we know what we're going to kind of be looking for, we'll step back a little bit and think of why do I really care about these? Why do I care about this information? As I mentioned earlier, I'm not writing my own code, but there's kind of three high level reasons why you would care. First, for reporting. If you're writing a manuscript or you're writing a paper, usually it's pretty good to put in there what you ran your code on. It's also important for documentation. If you run some code at some place, if you want to be able to reproduce it at a later date or have someone else be able to reproduce it at a later date, if you put the information about where and how it was run, you can do this. The next reason why we might want to understand what we're running on is for access. If you're initially looking to gain access to a new system or purchase a system, and you have a piece of software, you need to know what it's going to run on. Not all software is going to run on all locations. And not all software will perform as well on different types of hardware. So you can identify what your software is, you can identify what the hardware is and how it will run there. Another reason why it might be interesting is in the access ecosystem, there are many resources out there, but all of them are in pretty high contention. And so at least at this time, there's a really long queue wait time. So if you want to maybe switch systems, it will be interesting to be able to look and see where your codes will run. Also, how they're going to perform on the different systems. So you might want to look at clock speeds and cache sizes. And the last thing will be, if you're, again, coming new onto a system, you will need to compile your code for the system. By identifying the flags that are on the system, you can compile it to kind of fine-tune it specific for that hardware. The other is efficient utilization, and this is kind of my self project. Is the HPC resources are finite. So, and we do have long queue wait times. So if you want to run your job most efficiently, you want to know what you have and how you can fit it into a smaller box. And that's going to save you basically time and money. And it's going to make those resources available to other users if you're not holding them up. So in an earlier slide, I mentioned that HPC facilitates, and I'm going to highlight that word again, facilitates the ability to process data and perform complex calculations. But it does not 100% guarantee it. One kind of assumption people have is when they come to the supercomputer is that they're going to take their code and they're going to put it on a supercomputer, and because it's a supercomputer, it's going to run faster. And that's not true. The second thing is that if they just throw more hardware at it, it's going to run faster. And again, this is not true. The HPC applications need to be explicitly programmed to take advantage of that hardware that is there. So kind of to bring it down to kind of take an example of it. It's spring, so I was thinking flowers. You can tell by my examples where my interest lies. One of them is gardening. So if you're interested in planting a tulip, you can take a small hand shovel and you can plant that tulip. And generally, if you're planting one tulip, you have no time constraints. And even if you do have time constraints, even if you take, little Bobby from down the street who's 2 years old to dig that, it's not gonna affect you too much. But now let's say that you have a party tonight. So you do have a time constraint. You need to accomplish a task before a certain time, and you have more stuff to do. So again, we're just going to plant tulips. So the action is going to be the same. It's a simple process, but we want to plant a bunch of pots and we want to put multiple tulips in each pot. So at this point, we can still use our little hand shovels, but we probably are going to want to paralyze it and have lots of little Johnnies planting them. You can take that one step further, and in the Netherlands, where they plant, acres and acres of tulips that get distributed around the world, having a lot of little Johnnies is probably not going to be effective. So I think they're called combines, the big tractors that can dig up your dirt and plant your seeds for you. You're going to want to have a tool like that. Now, for the first three things I showed you, the action is always going to be the same. So you can very easily, it's repetitive. You don't need to go outside your thing. So you can have a tool that just needs to do simple, small tasks. But let's say you want to plant a garden. You want to start from scratch. So you want to have flowers. You want to put a pond in there. You want to have a pergola in there. And you want to put some bushes in there. Now, not only are you going to want lots of people, but you're also going to have different tools that can accomplish those tasks. So the last thing kind of steps away from doing this in parallel, but now we're talking about one big task. What if I want to have an oak tree in my yard? One could theoretically plant a seed, and 100 or so years later, you would have beautiful shade from that oak tree. But 100 or so years later isn't the time we want to have. We could also get a bunch of little Johnnies with their hand shovels, and in a month, we might have a hole big enough. But we could just get one big heavy-duty machine and one person to do it. So we get a backhoe. The backhoe can dig the hole, it can plant the tree, and we're done in an hour. So what all that really sums up to is you really need to make sure that you have the correct tool for the job. One other thing I should say, that you could use the backhoe to plant a single tulip, but it's inefficient and a waste of time and money. So again, coming back to use the correct tool for the job that's at hand. So the first step in deciding which tool to use is to identify the hardware that's going to be available. And so the first thing I always tell people when they come to a new system is always check out the user guide. This is just generally a good thing to always do. Not only is it going to provide you with details on the hardware that we're currently looking for, but it's also going to provide you important information about like backup policies and purge policies and job policies. But that's for a different discussion, different webinar. So for today, it's just going to provide you with kind of the theoretical designs on a system. So I say theoretical designs on a system because an HPC system can have a life cycle of up to 10 years. And so the system may change over time. But the user guide is normally manually updated. And so the systems folks, the user support folks, and the documentation people all need to be in sync. So there might be a little bit where the user guide is out of date, but again, it's going to give you a high-level idea of what's on there. But it's always good to reconfirm what's on that system. So we can use a couple tools. We can use some Linux tools, and we can also use the pseudo-file system to kind of find out more information about our systems. So the first command that I'm going to introduce is the lscpu command, and it's going to display information about the CPU architecture. The list I have here is not comprehensive, but it kind of gives some of the more important things. So it's going to provide you the number of processors, the processor type, the clock speed, number of cores per processor, cache sizes, instruction set architecture stuff, and so forth. So this here as an example, I ran lscpu on the Expanse compute nodes. And so the first thing I want to kind of highlight is the CPUs. And the CPUs is on Expanse. It has 128. So what CPUs represents is the number of logical cores, not physical cores, but logical cores. So it is an equation that is equal to the threads per core, the cores per socket, and the number of sockets. So on Expanse, we have 2 sockets. Each contains 64 core AMD EPYC processors. On Expanse, we do not have hyperthreading. I'll talk a little bit more of that later. So that's threads per core is equal to 1. So 1 times 2 times 64 is 128. Some other information that we find in here that is also very interesting is we can find more information about the caches that are available. I'm going to jump to the very end and also discuss flags. So it will also list the flags. And what flags are, it indicates what the CPU can support. So I highlight 2 flags here that I want to talk about more later, AVX and AVX2. But now I'm going to jump back to the NUMA nodes, kind of in the middle here on the below the sockets. The Expanse system has 8 NUMA nodes. So the NUMA node represents the memory architecture. And on Expanse, each physical CPU package contains, sorry about that. It contains a memory controller, and that handles part of the RAM. So as a result, not all physical memory is equally accessible to all CPUs at one time. But the physical CPU that can directly access the memory that it controls, but it's going to have to go through the other CPUs to access the other memory. So these NUMA nodes is how that's distributed. So you can see that with 8 NUMA nodes, the CPUs 0 through 15 are on NUMA node 0, 16 through 31 are on NUMA node 1, and so forth. Oh, wait, one more piece of information I want here. So there's one other piece of information that we didn't get from here, and that's how the cache to CPU association is. So we can still use the lcpu command to find that, but now we're going to send it with the E directive associated with it. So this gives us a little bit different preview of how things are set up. The first column is CPU and the CPU index, because it's actually an index of the thread of execution. On Expanse, we have 128, right? What I'm showing you is just the top 20 of them, but if you saw the full output, it would show 1 through 128. The second column, node, indicates what NUMA node it is. As mentioned, there's 8 NUMA nodes, so each node will have 16, I believe. Yeah, 16 CPUs associated with it. So you can see CPU 0 to 15 are all associated with NUMA node 0. It has 2 sockets. So 0 through 63 will be associated with socket 0, and the rest will be with socket 1. So the core indicates the actual so the actual physical core to which it belongs. On Expanse, we don't have threading, so you can see that the CPU is assigned to its own core. Oops, sorry about that. So the next thing we see is the cache here. So the L1 data cache, L1 data cache, L1 instruction cache, and L2 cache each have the cache is associated with each physical core. If this were a threaded machine, threads from the same core would have to share those caches. But L3 is a little different. You can see that L3 is shared by 4 physical cores. So we mentioned the hyperthreading before, or in our LCPU, we saw that threads per core were equal to 1. So we know on Expanse, we don't allow simultaneous hyperthreading, but simultaneous multi-threading or hyperthreading. But what SMT is, it's the ability for the CPU to split its physical cores into virtual cores or threads, and that allows it to increase the performance by allowing multiple instruction streams to run in parallel. So while Expanse compute cores or compute nodes do not allow this, we do have some nodes here, especially for data, our data mover nodes, which are especially used just for moving high amounts of data, that do allow SMT. So I mentioned that I wanted to go back and talk a little about the flags AVX and AVX2. So AVX stands for advanced vector extensions. And what they are SIMD extensions for the x86 instruction set architecture for microprocessors, specifically from Intel and AMD. Excuse me, hold on a second. So these instruction sets, they're additional instructions that can increase the performance when the same operations are performed on multiple data objects. So the AVX extensions can increase the floating point operations from 4 to 8. If you use AVX2, you can go from 8 to 16. And if you go to AVX12, you can go all the way up to 32. There we go. So what that means is that on a system, you can theoretically obtain 2x speed up from a non-AVX machine. You can theoretically get 2x more from that if you go from AVX to AVX2, and additional 2x if you go from AVX2 to AVX4. However, you will have noticed that we don't list AVX 512 on Expanse, but this is not a problem. Because I also mentioned that you need to be able to, just because something is available doesn't mean that your code can handle it well. So, and it's pretty difficult to get the speed up all the way up to 512. So the first thing you can see is if it's available. If it's not available, but your code can't handle it, you can use the tools of the lcpu command to identify other systems that do have it available for you. So I'm going to take one more sidestep before we go forward again and talk a little bit about, so this is another slide that Marty brought, that Marty had presented in his last presentation. And I wanted to bring it up again because not all the nodes on a system are equal. So if we're running the lscpu command on the login node, and if we run it on the compute nodes, it might not be the same. So if we're evaluating a system, we really need to make sure that we're evaluating the correct system. So just to kind of look on a high level again, the HPC systems have login nodes, they have compute nodes, they have data mover node, or they can have data mover nodes, they have management nodes, they're all connected by an internal network, and they all share a shared file system. So when the systems are designed, they're specifically designed to so that different things can handle different aspects of the thing. So the login nodes are specifically for users logging into the system. It's for them to do simple tasks such as editing, maybe doing small data transfers, and it's where you do your batch submissions. But the login nodes are shared by all the users. So by doing any like high taxing computational work is going to bog down the system. So what is needed on the login nodes may be different than what's needed on the compute nodes. Excuse me. The compute nodes themselves may not be the same. At SDSC, we have 3 different types of compute nodes. We have the regular memory nodes, we have the GPU nodes, and we have large memory nodes. And this is where we're going to kind of do our heavy lifting, where they do all the computational power. Reasons when they're different, you have to take in mind where you compile your code. So if you try and compile a GPU code on a login node, there's going to be problems. So you need to make sure if you do need to compile a GPU code, you can interactively log into a GPU node and compile it on the system itself. Now I'm bringing back in the data mover nodes because, as mentioned before, the data mover nodes are threaded or allow threading, so that it helps with doing these large data movement more efficiently. So I'm not sure if you noticed, but before I go on to, because I'll step into GPU next, but I'm not sure if you noticed, but the lscpu command did not provide any information on GPU. So, but we did mention that they are very unique, specific things that will be used for different purposes. So let's look a little bit at the differences. So the main difference between the CPU and the GPU are their functions. So a server has to have a CPU, and the CPU is going to handle all the tasks required for all the software on that server to run correctly. The GPU, on the other hand, will support the CPU, but it's going to perform very specific concurrent calculations. So what the GPU is really designed to do is to complete simple, repetitive tasks very quickly. And it's able to do this by breaking down the tasks into much smaller components. And that allows it to work in parallel. So I was kind of thinking about this, and I looked online a little bit, and it came up with an analogy that I really like for the comparison. This is another one of those things where it shows my interest, and it comes down to food. So if anyone's ever watched MasterChef, Gordon Ramsay has a bunch of people who are vying for his attention, and each week he has them work in groups to accomplish tasks. And so let's say this week's task is to, for a benefit, everyone, or the firefighters, you have 1,000 firefighters, and the firefighters need to be fed burgers. And two of the main goals of this is that all the burgers need to be the exact same, and all the burgers need to be finished at the same time. So theoretically, Gordon Ramsay could personally go and flip all the burgers, and he can probably make them perfect and the same, but he's not going to be able to have them all complete at the same time. In addition, because he's flipping burgers, he's not doing anything else in the kitchen, so it's probably not a good source of, or a good use of his time. So what he can do is he can delegate. He can delegate to his junior chefs. And let's say these are special junior chefs, and they all have 10 hands. So by giving it off to the 10 hands, they can all flip their 10 burgers in 10 seconds, and they can complete this task much more quickly. So let's look at the LCPU for the GPU node. As mentioned, there's absolutely no mention of GPUs on here, but you'll see that the CPU is still different. So on the GPU nodes at SDSC, there's 40 CPUs. There's still 1 thread per core. There's 20 cores per socket, and you have 2 sockets. Memory hierarchy is the same, although the size is different. And you'll notice the NUMA nodes and how they are distributed between 2 CPUs, or between the 40 CPUs, I apologize. So we can look a little closer. Now the CPU index is going to run from 0 to 31 for the 40 CPUs. There's only 2 NUMA nodes on these CPUs, so they're going to alternate between 0 and 1. The same thing for the sockets. There's still single thread to do for each physical core. So each physical core is going to be associated with its CPU. L1 data, L1 instruction, and L2 is also going to be associated with an individual CPU. But you'll notice that L3 is going to be shared between 20 of them. Yes, 20 of them, because there's 40 in total. So since the LCPU didn't provide us GPU information, if we do want to find out if a GPU exists, we can use the NVIDIA SMI command. The NVIDIA SMI command is specifically a command line utility to monitor NVIDIA GPU devices. And the command's going to provide us with the type of GPU, the number of GPUs available, how it's being, and how it's being used. Excuse me. Sorry, I think I swallowed a fly. And how it's being used. There are some other ways that we can find out if a GPU or there's a presence of any other accelerators, and namely there's 2 commands we can use, the LSPCI command or the LSHW command. So LSPCI is a utility that displays information about PCI buses on the system and the devices that are connected to them. Since a GPU is a connected device, you can search for the output from this system to see if it exists. Likewise, the LSHW is a utility for listing the available hardware devices. So both of those, if you run them without kind of filtering for anything specific, are very verbose. The LSPCI command has about 300 lines when I ran it, and the LSHW had over 3,000 lines of output. So you're going to want to filter. You can use your scripting, the scripting we learned in another one of our complex webinars. For the LSPCI, you're going to want to search for VGA or 3D. And for the list hardware, you're going to want to search for display or video. So I'm going to sidestep a little bit. All the information that we've kind of extracted using the tools has been coming from what we call a pseudo-file system. And it's coming from either the /proc or sys file system. So a pseudo-file system is really a file system that doesn't have any actual files. It has virtual entries that the file system itself is dynamically creating. So if we look in the proc directory, we can find information about the system hardware and any of the processors that are currently running. Processes, I apologize. So we talked about the kernel earlier, and so I just kind of want to step back and tie this in again. So the Linux kernel has two primary functions. The one is to control access to the physical devices on the computer, and the second is to schedule when and how the processes interact with those devices. So the proc directory file system is going to contain a hierarchy of all the special files that represent the current state of the kernel. And with this, it allows both the applications and the user to kind of explore into the kernel and learn more about the system at any given time. So if we're specifically looking for CPU information, we can get more detailed information by examining the proc CPU info pseudo file. As mentioned, LSCPU, we got all our information from this CPU info file, but the LSCPU kind of gave a summary data of all 28 cores in the node. So the CPU info is going to give us the information listed per core. So this is going to allow us to specifically look for on the node the specific information. So we can find the instantaneous clock speed for a particular node. Other information that it has is it can tell us if there's any bugs on it and if they were addressed. And it also gives us a lot more information, but we're not really going to go into that today for expediency, and we don't really need to know it for this topic today. So as I mentioned, on Expanse, there's 128 processors. So if we ran this for all of it, it would be, again, a very verbose output. If we just want to find the megahertz, we can look for that by filtering it down with head -5. It shows us just the top 5. And this bottom part is also is the rest of the information that's available. I wanted to show it to you, but again, not that important for today's discussion. Another useful pseudo file is the meminfo file. So this is going to give us a usage report about the memory on the system. The most important lines here are probably going to be mem total, mem available, and active. Something to keep in mind with HPC systems is that mem total is everything that's there. However, that may not be available to the end user because there are going to be some system processes that will take up some of that memory. So mem available is more the number that we're looking for when you're running your codes. But again, I would highly recommend that you take a look into the user guide. Specifically, I know that at SDSC for Expanse, we specifically list the max amount of memory you can request for a job. That is below the total that theoretically is available. The regular memory nodes have 256 gigs or up to. The large memory has up to 2 terabytes, and the GP nodes have 384 gigabytes. So you can see the differences between the 3 nodes that we have here at SDSC. We also, from the LSCPU, were able to gain some cache information, and that also comes from the pseudo file system. So to actually explore in depth for the cache, we can go to the sys devices system CPU, and there's going to on any given node, and there's going to list all the CPUs that are there. You can drill further into each of the CPUs, and you can drill into the cache directory specifically for them. Now, in that cache directory, it's going to list all the cache that's available. It's kind of cryptic name, index 0, 1, 2, and 3. But if you go further into that, you'll see that index 0 is going to be associated with your L1 data cache, index 1 with your L1 instruction cache, index 2 is with your L2 cache, and index 3 is with your L3 cache. And you can kind of discern what those are by the individual files that are available. So you can see if they're shared. So CPU list, you can see what type is available. You can see the size that there is. And the last bit of information that you're going to find useful when running codes is identifying any SCSI devices. Now, this is really worthwhile for you if you're running on HPC systems, is that there may be a local scratch available on the cores themselves. And by using this, you can make your code run faster. So, but you can use the lsscsi command, and it will show you that this particular place has an NVMe flash drive. So now we're going to take a closer look at the available file systems and how to evaluate their usage. We can do this in a couple ways. We can kind of do some high-level evaluation by, again, using the pseudo-filesystems. We can also use some Linux commands, but also if a system has specific file systems, the file systems themselves may have specific commands that you can use to evaluate them. So from a system level, we can review what is available and mounted in the proc or the etc pseudo file systems. We have proc file system and etc mtab. So the proc file system is going to display all the file systems that are currently supported by the kernel, and then it'll also show if they're currently mounted on your system. This is going to be a longer list than the etc mtab file. The etc mtab file will show you only what is currently mounted on the file system. So if we want to find out more specifics of what is really mounted, we can use the df command. So the df is going to report how much disk space your file system is using. It will primarily check the disk usage on all the mounted file systems. So if you don't specifically say you just want a particular file system, it's going to give you everything. In the output I have here, we're only showing selected file systems. So the other thing is that by default, the DF is going to show everything in 1K blocks. To make it easier to read, I am using the -H directive, which means human readable. So we see it in gigs and terabytes and such. So when we run the df command, again, this is on Expanse, we can see that it has a local scratch file system on there. We can also see that the software stacks are available to you. We have at SDSC a community and an SDSC maintained software stack. We also see that we have a Lustre file system available to you. And while it's listed that we have two, there's Lustre Scratch and Project File Systems. They do have different retention policies, but you can see by the size used, available, and used percentage that they are evaluated as one file system. The other important file system is your home file system that will also be mounted. The du command, on the other hand, is very useful for understanding your particular disk usage. We here at SDSC and the user support team use this very often. One of the common issues we get as tickets is that users say, I requested 2 terabytes of project storage, and it's telling me that my file system is full. And while we're fairly certain that they're using the wrong file system, the first thing we usually do is run the du-h command on their home directory to see if they've exceeded their 100 gig limit. Some other really useful commands to use with du is the time. So if you need to clean out files, you can use this time to see the last modification of any of the files in your directory. That might help you decide if it's useful and you can delete it altogether, or if you just haven't used it in a while, if it might be time to archive it and move it to a more persistent storage area. As mentioned, summary is a nice tool. Instead of giving you individual bytes, it will give you the high level for the directory. It'll show you everything in there. -H is human readable, again, makes it nice and easy to read. And -A lists all the files and directories in some given file path. So one of the things that really makes HPC is the networking and the connectivity between the compute hardware and the storage. And what this does is it really allows you to scale up your codes. The interconnects are designed to provide inter-process communication among various individual servers, and that allows the compute nodes to behave as one single large system. So while the processor speed, the memory, and the number of nodes in your cluster is really important, the other thing that's really important is the performance of your interconnect. So interconnect is really referring to the cabling and switches that are used by the nodes to communicate with each other. So while it's necessary for every cluster, it becomes really, really important when you're trying to run really highly parallel codes and where the calculations are going to be split among nodes, but they still need to be solved simultaneously, rather. So there's Ethernet, 10 gig Ethernet, and InfiniBand. So Ethernet basically or generally has transmission speeds of 1 gigabit. As the name alludes to, the 10 gig Ethernet is about 10 times faster, and it operates at about 10 gigabytes per second. And InfiniBand is, again, faster than that because it has both low latency and fast speeds. And on average, I think I tracked down that it's about 40 to 56 gigabytes per second. So we can find out what networking we have by using the sbind IP command. The sbind IP link lists all the network interfaces. So again, on Expanse, this is what the output would look like. That top thing, LO, stands for loopback device. And so a loopback device is a virtual interface that's always up and reachable as long as at least one of the IP interfaces on the switch is operational. So this is really important for our systems, guys. The EN at the beginning indicates that it's an Ethernet, and the IB indicates that it's InfiniBand. So at this point, we're going to slightly transition from evaluating what's available to kind of monitoring monitoring the hardware and how they're doing. So the first thing we're going to look at is the top tools. We're going to look at top, ATOP, and HTOP and explore. We're going to use them to kind of explore the active Linux processes. And then I'm going to discuss, I think, 5 more tools where top, HTOP, and ATOP are kind of dynamic. They're constantly updated. I'm going to do more static tools in MPStat, SAR, Free, PS, and we're going to look again at NVIDIA MPI, SMI, I apologize. And then I'm going to finish up this section with, again, we'll look at how you can evaluate how your particular job is using the hardware. So the top, HTOP, and ATOP, they're used to analyze the load of a server that's running on Linux. ATOP is a standard utility. It's installed on all Linux versions by default. HTOP, top, HTOP, and ATOP will all provide similar information, but the differences are how you can interact with them. And so HTOP and ATOP you can interact with, and ATOP also allows you to do logging. So let's look a little closer at the top utility. So why might we want to evaluate the processes? Why would we want to use top, ATOP, or HTOP? And you can really see what the system is doing and how it's being used. So you can see things like how many of my processes are running, how many of other people's processes are running. Very often, if the login node is starting to crash, we can check on there and see who's running on there and who's running something they shouldn't be running on there. You can see the states of the processes that are on there. You can see which cores are being utilized. You can see if there's competing processes. You can see how much memory they're using. You can kind of see over time how memory is being used and if there's a problem. And you can also see information about threads. So by default, on the top command, this again, it's provided by default with the Linux system. It will report to you, and it's report the processes that are available. It reports it by how much CPU is using. So top usage at the top, and it goes down. By default, it just shows the processes. It doesn't show anything about the threads, but you can see thread information if you use the -h command. Also, by default, it shows information for all the users. If you specifically want to just look at information for yourself, again, on the login node where there's lots of users, so you can use when you launch it, you can use the -u username command, but you can also, if you have it running, you can sort, you can dynamically sort. And so you can see the individual users grouped together if you use the U command. The other useful is the N command. So there will be lots of processes on the system. Many of them are systems. Some of them may not be using the CPU at all. So if you just want to see like the top 10, you can use the N command to see who's most heavily using the system based on CPU. Again, you could switch that, and you could use it by memory instead by using the capital M. By default, it provides the information listed on that and that last, the top high level bullet there. So process ID, priority, nice. And this is generally very, very useful information, but if you want to, you can manage those fields, and you can toggle the fields with the F command. The one other, well, I don't know, I guess it's the command or the control C, is to show you the full path of what's what the process is running. And I always find that interesting, because not only can I find the user who is running the command, but I can also see where it's being run from, and I can go back and maybe fix it. So here's an example of running the top command. So general information about the system is going to be displayed in the top part of the window, and the running processor is going to be displayed in the bottom. Information that is interesting is how long this particular node has been up. This one was up for 60 days. It currently has 1 user on it. The load average shows the load average for the last minute, the last 5 minutes, and last 15 minutes. Yes, 15 minutes, or 15 minutes ago. It'll show you information on all the tasks that are kind of summary information on the task. It'll give you statistics on the CPU, memory, and the swap. And the bottom half is going to show you the individual processes that are running on there. So what we see here listed are 16 processes. You can check how much the memory usage that they're using and the CPU usage. It's also interesting to note how long they've been running. In some cases, we can find that there's jobs that have been running for days and days and days, where most likely people have forgotten that they're running. So the HTOP utility is not built in like top, so it needs to be installed in your server. And the output of HTOP is going to be kind of structurally the same. So the upper part is going to be the information about the system and the CPU load and RAM that we saw before. And the bottom half is going to be the list of processors sorted by the CPU load. So as mentioned, the HTOP and the ATOP has a lot more flexibility and a lot more interactive abilities with it. So it allows you to do system monitoring. It allows you to view the process. It also allows you to do some process management. So to see everything that you're able to do, you can type F1 and it'll give you the help command on the bottom there. You see all your options. Some of the commands that I use frequently or I find useful are the M, so I can search for memory. I can also use P to sort per processor, T to sort by oldest first, and also the U to sort by particular user. The ATOP command, again, is a tool for monitoring system resources, and it's going to display the load of the system resources at the process level. It can be useful for diagnosing floating errors. It also allows you to keep logs. So this is different. It allows you to keep logs on the system and allows you to monitor work process over a period of time. So for this command, that's similar. By default, it orders by CPU usage, but you can toggle that to show memory usage. You can also use a -D to show disk usage. and the AU to show processors per user. So the MP, now the next four are going to be where top command was dynamically loading, and so it's constantly switching. The next five commands, I think it is, are kind of static, and they will show you a snapshot of the system at a given time. So the MP stat command is going to be used to report processor-related statistics. It can display the statistics of the CPU usage of the system and the information about the CPU utilization and the performance. So when you run the MP stat command, you'll see two sections. The first is going to display what the system configuration, and the second section is going to display the utilization statistics. And the utilization statistics are displayed in intervals at any time. But again, you should note that it's going to show the statistics for all 128. That top row there shows all, so it's kind of an average of how the system is kind of overall. But you can scroll down and you can see all for the individual CPUs as well. The SAR command stands for System Activity Report and reports on the various system loads on a system. And it kind of allows us to monitor the Linux system resources like CPUs, memory, I/O devices, file systems, network, disk usage, processes, threads. What I found interesting, you can even kind of evaluate the battery performance. The SAR information is pulled out of the proc file system. Some of the useful things that we can find here is you can find memory usage, you can find file system usage, and you can find file CPU usage. So the Linux free command is going to display the total amount of free and used memory on a system. So this also includes the physical and the swap space and the buffers and the caches used by the kernel. The information is gathered again from our pseudo-file system. This time it's going to be, or the pseudo-file mem info. And the main column of interest here is really going to be that last column available. And the last column is going to estimate how much memory is available for starting any new applications without swapping. The PS command returns the current what is currently active on the system. And it's like top, but it has additional info. And also this is going to be a snapshot of the current processes, where the top command again updates constantly. So I'm going to quickly revisit the NVIDIA SMI command, but we're going to look at it from a different perspective. Before, we are looking to see if the GPU existed, so we could see that it existed and what type of file it was. Now we're kind of going to look at it from a monitoring standpoint. As you can see, there's actually no GPU processes running, and I left it in this state because well, I wanted to kind of reinforce that you need to make sure that you can abuse the system properly, and that if you don't need GPUs, you shouldn't use GPUs. So in this command, I simply got an interactive session. I ran the NVIDIA SMI, and since I wasn't running anything on the node, it shows that there's no processes running. So I highly encourage folks that if they're using GPUs, they can once they get the GPU and it's assigned to them, they can interactively log into that specific node and run this command to see how their code is taking advantage of the GPUs. So the next two tools are specific to evaluating your jobs utilization on the hardware. These two tools are specific to the job scheduler that is available at SDSC. So this is another resource that you have at your disposal, the schedulers. So the two tools I'm talking about is the Ceph command and the saccet command. The Ceph command actually stands for Slurm Job Efficiency Report. And this command should only be run on jobs that didn't run out of memory somewhere in their job, and on jobs that are completed. If you run it on a job that ran out of memory, or is still running, the output is not going to be accurate and not worth your time. The other command, and sacket is a really powerful tool for evaluating your pending jobs, your running jobs, and your finished jobs. And while I don't have enough time to go into large details on how to use this command, again, you should look it up, and in the later slide I provide a link to how you can use this command more. We just don't have time to go into it today. It's very useful. I highly recommend everyone looks into this command for evaluating their jobs. Unfortunately, both of these commands do not provide any information on GPU usage. It just provides on CPU and memory. So we've probably gone a little deeper than is necessary, but I hope that we managed to hit on kind of our agenda items and at least bring awareness to the various tools that are going to be available to you and how you can use them to evaluate and monitor your system and your jobs. I strongly encourage everyone to use these tools to do some monitoring to make sure that they're using their resources efficiently and that they're saving their own time and money. The next 2 slides is just a cheat sheet. It provides all the tools that we went over today. And I mentioned that I was going to give a couple links to help with the Ceph and sacket commands. I also provide a link to the training catalog that we have. The training catalog not only contains the complex webinars that we have, but any other training that's available here to us. Oh. And with that, I want to thank you all and open it up for discussion.